Hello, Chemistry. This is the Organic Chemistry chapter, lecture video 4, and we're going to be talking about reactions in organic chemistry. So, specifically looking at reactions that involve alkanes, alkenes, and alkynes. So, one of the reactions that you guys probably should remember from Chem 1A is the combustion reaction. This is where we react an organic compound with oxygen to form carbon dioxide and CO2. Another type of reaction that we'll be going over are halogenation. This is also known as a substitution reaction, and effectively what goes on in this is where we replace one or more hydrogen atoms that are on a organic compound with a halogen atom, like chlorine, bromine, and so on. Now, we're not going to go very deep into most of the reactions in organic chemistry because it is a 2-semester long class that covers all those in depth. But here you go. Usually we react an alkane or an alkene-alkyne with chlorine gas or bromine liquid or iodine, and we lose one hydrogen, and we form usually HCl or HBr, hydrogen attached to a halogen, and an organic compound with an additional Cl, losing one of the hydrogens in that place. This reaction generally only happens with intense heat or using light as a catalyst. If we do this again, we can continuously add more and more chlorines onto it. Basically, as long as the chlorine is the limiting reactant, we'll only get one chlorine added. If it's the excess reactant, basically we can get up to 4 chlorines added to the carbon in methane. And in the ethane, we could get, technically 6. But it can happen to any organic compound. Let's talk about alkenes and alkynes. We're going to talk a little bit about what we call addition reactions. This is when molecules add on either side of the multiple bond, either the double bond or the triple bond. So in a symmetrical system, we have something like this, where we have this double bond here, and we have the Cl and the Cl here. They're both very symmetrical, right? 2 hydrogens on this side, 2 hydrogens on this side, a Cl here, a Cl here. So when you do this, you can only form one product with both the reactants being symmetrical. The Cl you can kind of think of as coming in here, attaching there, and the double bond going away, right? And this bond breaking. So we get this guy with the 2 Cl's on either side of the double bond and the hydrogen still present. If we have a symmetrical alkene but an unsymmetrical reagent, something like this, now we have HCl here. The H will attach to one side, the Cl will attach to the other. This guy goes here, this guy goes here. The double bond loses, we break that bond. And we get CH3HCl, or CH2Cl. Again, the Cl, we don't have to use Cl here. We could be using Br, F, whatever. Doesn't matter. Now these ones, you only get one possible product with both of these, but if both things are unsymmetrical, things can get a little bit more complex. For instance, if we have a completely unsymmetrical system, we have this is unsymmetrical and this is now not symmetrical, right? We have these 2 hydrogens here, but we have a hydrogen here. We don't have a hydrogen there. This is not a symmetrical alkene. So when this guy attaches, if it attaches it this way or it attaches this way, we're going to get different products, right? So in the scenario where we attach like this, where the hydrogen goes here and the Cl goes there, we get, and we lose this and this, right? We get this product. But if we have something where we have the Cl here And the H here, the H attaches there, the Cl attaches there, we lose the double bond, we lose this bond, we get this product. So which one's more favored, we should be able to tell, right? How do we know which one we get? The real answer is we get some of both, but there is going to be one in majority, the one that we form way more of. So how do we predict which product will be produced in the majority? It's going to be this guy, and let's talk about why. So in that scenario, we use what's known as Markovnikov's rule. Markovnikov's rule, sorry. When a polar reagent like HCl, polar, is added to an unsymmetrical alkene, the positive end, i.e. in HCl, this is the partial positive, this is the partial negative, positive end of the reagent adds to the carbon that already has the most hydrogens. So if we look back on this, here's our hydrogen. On this carbon there are 2 hydrogens. On this carbon there's only 1 hydrogen. So this hydrogen is going to add here. The Cl then will add in the other position, which gives us this product. And you should know this rule and how to do these. So next we're going to talk about functional groups. Now functional groups are a way of organic chemists organizing all these different types of organic compounds into groups that have similar chemical reactivity. Now, other than alkyl groups, there are these specific substituents that tend to show up a lot, and we call these groups functional groups. Compounds with different functional groups usually have different reactive or chemical properties present. Now we're going to cover a number of different functional groups, and each one has a different name. The first group that you may have already heard of is known as an alcohol. Now this R group here, this R is just simply saying, hey, this OH group is attached to a carbon chain. R is usually a representation of a carbon chain. So for instance, I could draw a alcohol like this, and this would be simply 2-butanol. Now we name them differently as well, but this is a butane chain, a 4-carbon chain with an OH attached to that chain, and this is known as an alcohol. Ethers are another type of functional group. In this one, we have 2 R groups sandwiched. In between them is an oxygen. So another example of this would be where we have an O with 2 carbon chains coming off of it. This is known as diethyl ether, this specific compound, and this would be an example of an ether. Another functional group is known as the aldehyde, and this one is a little bit tricky. Again, we have this R group, but this time the R group is attached to another carbon. And on this carbon, we have 2 other groups. We have an H group attached to it and an O. Now, aldehydes have a double bonded O in them, so when we draw them, we could have something like this. Now, we have the C as part of that group, and this is my aldehyde. So these 3 elements are the same ones that I have in blue over on the left there. Another functional group that we'll cover is ketones, and ketones are kind of like an aldehyde, but they're in the middle of the chain instead of at the end of the chain. So if we have something like this, this would be known as a ketone, where we have that double bonded oxygen, and on either side we have this carbon, but on either side we have other carbons on either side of the other carbon. And this is known as a ketone. Carboxylic acids are another functional group, and these are similar to aldehydes, but with instead of an H coming off of the carbon, we have an OH group. And so if we wanted to draw a carboxylic acid, we would draw something like this, where we have a double bonded O and then an OH, and right there is our carbon. So again, here's this carbon right there,
the OH group, and the O all referenced in that like kind of shorthand. Next, we have something known as esters. These are different from ethers, but they're kind of like the combination of an ether with a ketone. So if we wanted to draw this one, it would be something like this with an O group there. So another way to do this, right, maybe make it a little clearer, is this. Now this group here is the ester. Anytime we have an O sandwiched between two carbons and next to that oxygen is a double bonded oxygen on the carbon, then that would be an ester. And so we're going to be looking for these groups within compounds so that we can for sure pick them out. They all have different reactivity, and it's going to be a very important thing that we have to understand when we talk about organic compounds in the next semester if you have to take OChem. For this class, all you need to be able to do is identify them in a compound. Now, there are technically two more groups of functional groups that we have not covered, and they involve nitrogen. The first of them is known as an amine. An amine is a functional group where we have a nitrogen attached or bonded to the carbon chain. However, there are technically three different types of amines. We have a primary amine, a secondary amine, and a tertiary amine. And really all these just vary with how many carbons are attached to the nitrogen. So if we just have a group of carbons attached to NH2, we can kind of see here that only one carbon is attached to my nitrogen with a bond, right? This carbon here is bonded to the nitrogen. And so this is known as a primary amine because there's only one carbon bonded to my nitrogen. If we had a secondary amine, we might have something like this, where now we have a carbon here and a carbon here, both bonded to the nitrogen, which means we have two carbons bonded to that nitrogen. This is known as a secondary amine, secondary for two. The last one is known as a tertiary amine. Something like this would be if I have, let's say, 3 carbon chains now bonded to my nitrogen. And you can kind of tell that each time we add more carbons to the nitrogen, we get less hydrogens on that nitrogen as well, right? So these all technically have a lone pair on nitrogen if we remember our Chem 1A Lewis structure stuff. And so as we add more bonds, we have to lose hydrogens when we have these amines present. So this last one is the tertiary amine because we have 3 different groups of carbons all bonded to the nitrogen. Okay, our last functional group that we're going to cover is known as the amide or amide. I honestly don't know the correct pronunciation. I've heard it both ways. I think everybody just does what they want with this one in terms of pronouncing it. I personally call it an amide, or I'm sorry, an amide, but I've heard amide quite frequently too, so, you know, use whatever you want. Amides are similar to amines as they have nitrogen. However, they're kind of like a combination of an amine with a ketone, like an ester. So when we draw an amide, we are going to have a double bonded O next to a nitrogen bound to the same carbon that has the double bonded oxygen. Now this whole group here is my amide. This specifically that I've just drawn is a primary amide or amide. And we know that because there's only one carbon bonded to that nitrogen group. But we could have secondary amides as well. So if we have something like this, where we have the nitrogen, but then we have another carbon group coming off of it, this would be a secondary amide. And we could do a tertiary as well. So something like this would be the tertiary amide. And so this is our final functional group that we'll be covering in this class.
Okay, so let's talk a little bit about the alcohol functional group because they're kind of interesting. These are compounds with the OH group. We're going to learn how to name these. It's the only functional group that we're going to learn how to name. So alcohols, when we name them, we pick the base chain that contains the alcohol, the longest chain still, but it has to have the alcohol attached directly to the chain. We number it the same way we do double bonds, so we pick the numbering so that the alcohol group is on the smallest number carbon, and we change the base name to OL instead of E. So like for instance, if we had a ethane chain with an alcohol on it, ethane would become, we lose this E and we replace with OL, so ethane becomes ethanol, which is the one that's in, alcoholic beverages. Methane would become methanol, which is the one if you drink this, you die. Or go blind, depending on how much you drink. So we can assign numbers with the alcohol being the lowest, like I mentioned, and the number for the alcohol always goes in front of the base name, just like we do with double bonds. So let's do an example. We want to name this guy. So we got to count this chain because it's the longest. This is not a carbon. It's the bond to the oxygen. So we start counting here. 1, 2, 3, 4. So this would normally be butane. But since I have that alcohol group, I'm going to erase the E and put OL. I'm going to put 1 butanol here. And I do have a methyl group. So this would be 3-methyl-1 butanol. Or that. Let's do one more. So in this case, again, longest chain. This is my longest chain. I have a methyl group here and a methyl group there. My alcohol is going to be on carbon 2 because 1, 2, 3, 4, 5, 6. And so I have hexane would be my normal name, but we got to lose the E, change it to OL. So this becomes hexanol, and the alcohol is on carbon 2, so it's 2-hexanol, and then it's dimethyl, and in this case we have 2, 3. Ugh. Hold on, I'm going to make some more room for myself on this. So we have 2, 3 dimethyl, 2-hexanol. All right, I think I got, that might be this one. Yeah. Okay, so let's talk a little bit more about reactions with alcohols. Alcohols can be either oxidized or reduced. Now, this isn't in the same context as electrochemistry. While the definition still holds, oxidation is when our oxidation numbers increase, and reduction is when our oxidation numbers decrease. With OChem, they don't really want to deal with all that, so they define it slightly differently. Oxidation in organic chemistry is simply the gaining of an oxygen or the losing of a hydrogen in the organic compound. And reduction is the opposite, the losing of an oxygen or the gaining of a hydrogen. The first oxidation of an alcohol is going to create an aldehyde, right? So, for instance, if I have some type of, or a ketone, it really depends on the position, right? So for instance, like if I have ethane, and here's my OH group, if I oxidize this, I'm going to lose this hydrogen. The electrons there will come here, and we'll get that. There will be a hydrogen here that we're not showing, but that's an aldehyde here. That happened because the OH group was at the end of my chain. If I was in the middle of the chain, for instance, I had my OH group here, then when I get rid of this hydrogen, we get a ketone because there's a carbon here and a carbon there. And I think I have a picture example too to kind of give you guys. All right, so here's the oxygen at the end of the alcohol at the very end of our chain. This forms an aldehyde. Here's the alcohol in the middle of the chain. It forms a ketone. The oxidation of an aldehyde, so let's say I start with this guy, will produce a carboxylic acid. But instead of getting rid of a hydrogen here, what we do is we add an oxygen. So for instance, we oxidize this, we get this OH group here. This whole thing becomes a carboxylic acid. And you should know this about these. Like if I asked you, hey, if I oxidized this alcohol, what would I get? Draw the structure. Or if I oxidized this aldehyde, what would I get? Draw the structure. Or if I reduced this carboxylic acid, what would I get? Draw the structure type scenario. All right, so
the last topic in organic chemistry we're going to cover is polymers. Now, there are a number of uses of polymers, but what are they? Some of you may have heard of some polymers out there like nylon or Kevlar. Polymers, what they really are long chain compounds, usually made up of carbon, but other things as well, which are really kind of neat because they have this repeating unit that just repeats over and over and over and over again in this long chain. These repeating units are known as monomers. Now, polymers have a huge number of uses. There are both industrial polymers and natural polymers out there. Some natural polymers are things like DNA, starches, and proteins, whereas some industrial polymers are plastics, really. Kevlar, bulletproof material, plexiglass windows, PVC, which is typically used in plumbing, specifically most often in like irrigation, and there are so many more out there. To give you some idea, here's the actual chemical structure of Kevlar, and you can kind of see I have the monomer bolded here. This is the monomer, which is our repeating unit in Kevlar. And one of the things that makes Kevlar so strong in its ability to kind of prevent bullets is all of its hydrogen bonds. So all these dots between an oxygen and hydrogen, or a nitrogen and a hydrogen. These are all the hydrogen bonds in Kevlar, and that hydrogen bonding really holds the different polymer chains really tightly together. This is PVC, or otherwise known as polyvinyl chloride, and again, it has a repeating monomer, and you can kind of see it here blocked out, and this monomer just repeats over and over and over again. Okay, well, that is the end of our organic chemistry chapter. If you have any questions, as always, please feel free to ask me in class or come to my office hours.